Now, I'm pretty excited to introduce Dr. Vinayaka Murthy. So Dr. Murthy is the Duke Energy Distinguished Professor of Power Engineering and Electrical and Computer Engineering at Clemson University since January 2012. Uh, Dr. Murthy has held a prior position as a professor at Missouri State and Missouri University of Science and Technology from 2002 to 2011. At Clemson, Dr. Muthi is the director of Real-Time Power and Intelligence Systems Laboratory. He holds the position of an extraordinary professor in the Department of Electrical Electronics and Computer Engineering at the University of Pretoria, South Africa. Dr. Muthi received his PhD and MS engineering degrees in electrical engineering from University of Natal, Durban, South Africa. Received his bachelor's from with first class honors in electrical and electronics engineering from Abubakar Tafawa Balewa University, Bauchi, Nigeria. Dr. Muthi also holds an MBA degree in entrepreneurship and innovation from Clemson University. Dr. Muthi is the recipient of 2004 USF Career and 2007 US Office of the Naval Research Young Engineer Award. The list is really big, so I'll keep it really short. If you want to go deep into the background, we have attached this speaker bio with this call, with the talk. But looking for, you're ready to jump into the talk. I'll hand it over to you, Dr. Muthi.
Yeah, thank you, Krishi and Wally. Hopefully, you all can hear me.
Yes.
Yeah. All right, great.
No
So
problem.
this, yeah, for me it's noon, just a little after noon here. So today I decided to talk on sustainable AI, and I think that will be important as we are looking at big data and big data analytics, and we all know today analytics is driven by AI, and so therefore this topic will be very important as we deal with large data sets, and of course for us is power systems operations. So the presentation is outlined as follows. I will have a quick introduction. Then I'll get into cellular computational networks, and some of you who might have listened to some of my talks at the PS conferences, PS general meetings, may have come to know about cellular computational network. Otherwise, today you will get to find out what these CCNs, short form for cellular computational networks, are. And then I will get into some, a couple of selected case studies, but there are numerous papers you can find on my work in this area of CCNs, and then I will summarize the presentation. So to begin with, I think, we are dealing with complex systems. And for those of us that are familiar with complex systems know that complex systems are made of many components, and this basically interact at different levels with each other. And then we basically have a network, yeah? And this network basically consists of nodes, and these nodes could represent components, it could represent subsystems, and of course, the links between these nodes or components or subsystems basically represent the interaction between the different parts of the network. So each of this node may or may not have different kinds of different levels, complexity of behavior. And intrinsically, to model the network behavior, you will have to model the behavior of the nodes and the components. And because all of this network behavior depends on, it's basically a nonlinear sum of the different behaviors of the nodes and the components. And not only are we dealing with this network and the internal dynamics of this network, but also this network has external dynamics. This external dynamics comes from the environment in which this network interacts. So now we see the complexity is even more, not just only the internal interactions within the network, but also the network interactions with the environment. So that adds even further. So we basically, in a nutshell, we'll be seeing distinct properties when we look at this different complex systems. So in the very beginning, you see a model of the brain. and you are going to hear some burst sounds. And these burst sounds are basically how the neurons in the brain, as they go through learning process, they undergo what is known as a burst phenomena. This is a nonlinear, spontaneous behavior that happens. The brain is a very good example of a complex systems. And of course, we had a project back in 2008. We called it Brain to Grid Project, funded by the US National Science Foundation, one of the 4 projects from cognitive optimization, from neuroscience to neuroengineering. And this was a collaboration that I had with a professor at Georgia Tech in the biomedical engineering, a neuroscientist, where we studied in vivo brains, living neural networks. And these are some of the videos taken from that project. The other examples of complex systems are basically you have your air transportation network, and I think many of us, all of us probably fly, and you know that what happens when there's a delay in a flight, or even when we have a weather problem that causes a number of flights to be delayed, and how that cascades and impacts that network of air traffic and air transportation. And then, of course, on the right, you see the sub-transmission network of the continental U.S. sub-transmission levels and higher, and you can see it's quite dense on the southeastern side. So today we say that the North American power system is the single largest machine built by man, besides the internet, which has now overtaken. So we are dealing as a power system. And the North American power system is a very complex network. So all these properties that I've explained of a complex network is seen clearly in the power system. So as a result of all the deployment of, we know those working in power system operations, we have deployed a number of phasor measurement units, synchrophasors, a lot of smart meters, and lots of IoTs, Internet of Things. And all of this generates lots of data, 10 to the power of 18 or more bytes of data periodically. So we are dealing with complex networks generating tons of data, right? So not only is the amount of data being generated huge, but also the data volume and the data dimensionality also presents challenges to our methods, computational methods, for scaling up. And so, many of these complex systems are basically multiple input, multiple output systems. So what we are doing is, when we learn from this data, is we are doing MIMO learning. And the challenging thing with MIMO learning is that we're simultaneously trying to predict multiple outputs given a change in an input or a set of inputs. So the dimensionality we are talking about can be quite large. So many of these problems of learning from data today is being handled by advanced AI algorithms, such as deep neural networks, deep learning systems. And again, this slide basically shows us, again, what I've explained, the smart grid or the power system as a complex network, and all the data sources that you can see at the different levels of the power system, starting from the large generations to the transmission, to the distribution, to the microgrids, to the customers, even to the electric vehicles that connects to the charging station, or the bidirectional inverter that can charge as well as discharge. So the top part of the slide basically shows us all the different information sources, data sources that you'll have to work with in order to keep this power system at 50 hertz or 60 hertz, depending on what frequency your grid operates at. So different generation data, different energy storage, pricing, all kinds of voltage and current phases. So we are dealing with big data. And of course, big data can be described by volume, velocity, variety, veracity, value. And then, of course, in the midst of all of this is the visualizations that are created in real time to interface with the humans and the system operators at the different control centers. So this is a really a cyber, physical, social, system, right? Because we also have humans in the loop. We have humans as the consumers who are interacting with the grid. So the dynamics is just more than the physical system dynamics, but also human dynamics. So we have a lot of data. So the whole thing here comes down to how much of this complex data can be operated in a meaningful manner, time-critical way, such that we are able to maintain an optimal operation and management of the power system. Of course, the modeling of such systems, people have looked at, the traditional way has been nonlinear differential algebraic equations to model power systems. And now large-scale neural networks have been effectively used to learn solutions of these differential algebraic equations. The data needs to be turned into information, information into knowledge, and knowledge into understanding for us to have a successful operation of the grid. So AI, also known as computational intelligence, the IEEE doesn't have an AI society. It has a computational intelligence society. And computational intelligence can be basically defined as computational models and tools of intelligence that can take this large raw numerical data from all the different kinds of IoT, process them using some parallelism and also some sequential pipelining to generate just-in-time responses. If dispatches have to be done every minute, then the solutions are there. And these solutions are highly fault-tolerant. And some of the soft paradigms used to realize this computational intelligence can be classified as mentioned on my slide, neural networks, fuzzy systems, evolutionary computation, swarm intelligence, artificial immune systems, and then, of course, the hybrids of such software paradigms, because no one paradigm is superior to any other on all different kinds of problems. We know the lunch-free theorem. So the hybrids become really valuable. So today's AI is basically the brain of today's AI with all the large language models, LSTMs, the transformers, and so forth, is basically neural networks. Nutshell, the nut and the bolt is basically a neural network. Yeah. And the neural network is inspired by the brain, right? Brain-like intelligence. So a simple neural network can be shown here as a multi-layer perceptron, a feed-forward. Of course, we have different architectures. For illustrative purposes, I've shown here a three-layered network with an input layer, a hidden layer, and an output layer. We have an input X and an output Y with a bias 1. And we can even simplify this and say that mathematically, we can draw this neural network as shown here, having a hidden layer with one neuron, and that hidden layer basically has a nonlinear function, in this case, a sigmoidal function. Such a network can be used to approximate a very simple nonlinear function y is equal to 2x squared plus 1, as shown by the graph here, and it can learn that. When we say the neural network undergoes training or learning, all we are doing is simply identifying the synaptic weights, in this case, W11, W12, V11, V12. Once we have gone through a set of input-output data of X and Y, then basically we're using an algorithm based on gradient descent, such as the backpropagation. We can figure out what these parameters are. Once these parameters, synaptic weights are determined, then we can easily write an equation for the output based on the input, right? So once we have this equation, we know that this is the equation that's equivalent to y is equal to 2x squared plus 1, which we have learned from the data. So in other words, after a neural network has been trained, it's no longer a black box, it is a white box, because now we know the parameters. So one of the misconceptions we have in the community is that neural networks are black box. I agree neural networks are black box only if the parameters are random. Once it's trained, then it's no longer a black box. We can extend this further to have more neurons, more inputs, and again, when you add more layers, we have a deep neural network, right? So a deep neural network simply has multiple hidden layers. And as a result of these several hidden layers and several number of neurons, we have millions of synaptic weights to learn. So instead of simply having W11, W12, V11, V12, just 4 parameters, now we have millions of parameters to learn. So that's what a deep neural network is, and a deep neural network can have multiple inputs, multiple output, and one of the learning could be more complex functions as shown here. So the mainstream AI today is using deep learning and deep neural networks. So we all know this is computationally expensive. Just have explained, we have millions of parameters to learn, right? We also know we need a large data set to train deep neural networks. And deep neural networks basically means that with large data set, large training time, is going to consume huge energy consumption. So we can simply say deep neural networks are energy hungry beasts, right? So the question is, when we are consuming a lot of energy in these data centers, right, to train, to learn to solve a problem, with a lot of data set, lots of training time, weeks of training time, megawatts of power dissipated over long periods of time, basically we are putting out a lot of emissions. And today there's 51 plus billion tons of greenhouse gases that are added to the atmosphere annually. And just to do a direct capture of this is going to cost about $5+ trillion per year, which is about 6% of the world's economy. So this is not sustainable, and it's not the best way to actually even carbon capture is also challenging. So this is not scalable, not sustainable. Efficiency and scalability of today's AI and machine learning approaches for safe and mission critical application is questionable. Okay, so the kind of AI that we have today and we are working on, is it sustainable? That is the question in front of us. So we also know the UN Sustainable Development Goals, and when we talk about today's talk, it is looking at 12 and 13, responsible consumption and production. So are we consuming energy in a responsible way, using a lot of energy to power AI data centers? Then the next thing is, of course, we understand if we don't power these data centers, this huge amount of energy from renewables, then basically we're going to impact the climate, right? So this is the question before us. So sustainable AI is defined as a movement to foster change in the entire life cycle of AI products, starting from the idea generation, the training of these AI models, retuning them to focus on improving performance, their implementation, how are we implementing them, the governance, all of this basically challenges the ecological integrity and the sustainability. Right? So today, sustainable AI can be thought of having two branches. One, AI for sustainability, which is what most of us are working on, right? We are trying to use AI in power and energy systems to improve sustainability, better solutions, better optimization, better integration of renewables. But the other branch is the sustainability of AI, the reduction of carbon emissions, the power consumption by the AI tools. Do we have AI tools that are energy efficient? That is what we should be looking at. We don't want to apply AI for power and energy systems where we are trying to improve efficiency by one step, and then the energy that we use to power these AI engines takes us 2 steps backwards, right? That won't be a good solution. So this brings me to cellular computational networks, right? So we all know about building blocks, right? Building blocks, those of us that have been working in power electronics basically know that power electronics is scalable from building blocks, right? Sometime back, the Office of Naval Research had power electronic building block, the PEPs, right? So building blocks. So can we actually build AI models from building blocks, right? So one of the common things when we think about building blocks that come to our mind is Lego, right? So many of us may have played with Lego, either us as a kids or our children or we know someone. So as you look at this Lego, you see the Lego comes in different colors, different shapes, different sizes, right? So how about using something like that, right? So Lego basically comes from Norway, right? Denmark, sorry. And it means in Danish, play well, right? That's what it means. So when you have these Lego pieces, you start building simple structures, and then eventually you get creative and you can build more creative, imaginary, more, can be even more innovative in building all kinds of different complex structures, all the way up to the Titanic, to the Taj Mahal, the Colosseum, right? All from this Lego pile, right? So can we have something like this to build AI, right? So this takes us to cellular computational network. Cellular computational network basically consists of cells, right? And each of these cells basically consists of three kinds of units: computational unit, a learning unit, and a communication unit. The computational unit basically is the algorithm, the computational algorithm that takes an input and gives us an output, whereas a learning unit is basically trying to learn the coefficients that govern that output function as a function of that input, right? So it could be a time series, it could be a neural network, and the learning unit is trying to learn this, the weights. The communication unit, as shown on the picture on the left, it's basically, this is one many topologies of CCN, where the cells are connected to each other. So the communication unit allows us to connect this different cells, like the Lego pieces connecting with the different Lego pieces, right? So if we can take a complex system, we can break it up into subsystems that can be represented by the cells. And the beauty of the CCN is that it can basically handle this whole complex system as a multiple input, multiple output. And each of these cells could have a single output, but have multiple inputs. And then we can look at the output of each cell as a function of the outputs or the interconnections between the other cells. So in other words, if you take a look closely with the CCN, we can basically, from each cell downwards is a deep neural network sitting there, right? This is just shown for this particular topology, but you can have different kinds of topology for the CCN. So a CCN is a directed graph. It's modular. It's an adaptive distributed computational engine for learning the dynamics of complex system. Okay, as the cells are all different cells are learning, so it's a learning of learning system. So you can consider each cell as a system or a subsystem, and then you have interconnections between them. And of course, you can have an n-dimensional D-layer CCN, which means that the CCN can be stacked. Okay, so the stacking allows us to build a hierarchical AI model, and you can have different each of this CCN, each of these layers of CCN can provide different kinds of things that you want it to do. Like you bring in the data and you can get an information layer, you can get a knowledge layer, you can get a decision-making layer, you can have your control layer, which is known as action layer. You can have all kinds of different things that you can build upon and connect the right cells to provide the right output that you want. So it is very scalable from an architecture point of view. To illustrate this a little further, I've put in here an example of a system with 4 inputs and 4 outputs connected in the topology shown here. You can easily model this by using a multi-layer perceptron and have 4 multi-layer perceptrons with 4 outputs. But the difference here is that the multi-layer perceptron can replicate this system provided the system is static. If the system dynamics changes, since there is no coupling between the MLP's performance will degrade. One way to solve that problem is to change that to a recurrent network, where you can capture the coupling. But the problem with the recurrent neural network is, for a 4 input, 4 output, it's fine. You have 4 inputs, 4 outputs. But the moment the system has 1 million inputs and 1 million outputs, then the recurrent neural network will also have 1 million inputs and 1 million outputs, and that becomes a deep neural network. And we all understand now the problem with the deep neural network. So one way to solve this is to have the cellular architecture. And the cellular architecture allows us to have a sparsely connected recurrent neural network with much fewer weights. So the weight matrix here is it is a sparse matrix. Therefore, we have fewer parameters to learn, less training time, and so forth. Yeah. So again, to look at this, another beauty of the CCN is that if you take a CCN with 4 cells connected in this topology, as shown here, cell 1 connecting to 2, and 2 connecting back to 1, 2 and 3 connected to each other, 3 and 4 connected to each other, 2 connected to 4, 3 connected to 1. If a disturbance happens at cell 1, based on this topology, at the next time step, that disturbance will propagate naturally to the cell that it's connected to, the one that's adjacent, in this case 2. From 2 at the next time step, it will propagate to 3 and 4 and then modulate. So this is how disturbance propagates even in our power system, right? So the cellular architecture, CCN, models that. And when the performance of any of the cell degrades, we can basically monitor the performance of the cell, and basically we can trigger retuning, right? So it is only a localized effort and not a whole centralized effort with like the deep neural networks. And you can see when this happens online learning, you can see how sparse the learning is. Some cells don't learn, and while others learn. So this is asynchronous distributed learning that takes place in the CCN. And that brings about a lot of energy savings to the AI model. So to summarize the CCN, these are some of the attributes. It is cellular, it's modular. You can operate that in a synchronous or an asynchronous manner. It's efficient and easy for learning. It can be implemented on distributed and parallel computing platforms. It is scalable, as I showed you. You can stack this up. And when one of the cells is affected for one or more reasons, the performance of the CCN undergoes a graceful performance degradation. Therefore, there's resiliency in the AI model. We talk about power system resiliency, but we also need AI resiliency. And last but not least, the focus of my presentation, it is sustainable because the energy consumption of this CCN is much low. Okay, so now I'll show you a couple of case studies here on the CCN applied to the power system. One is the voltage prediction problem. Okay, so here is a 12-bus network, and some of you may be familiar with this 12-bus network. And we want to model this using CCN, and that's the CCN counterpart of this 12-bus network. And you can see it's all the cells are basically having very small neural networks. For example, if you look at bus 1, it is just a 4 times 3 times 1, just 15 neurons. There's a very shallow neural network in each of these cells. Okay, and this table basically shows us using 11 cells, the number of inputs, number of hidden layer nodes, number of outputs, a total of 237 weights to model this network. Whereas if you use a standard single neural network, you will need to get the same performance of 468 parameters. So that's like half of that. And then basically the performance of these 2 neural networks, one developed by the cellular architecture and one by a single neural network, is shown in terms of a metric here that we use as dynamic voltage index, showing how good these networks are able to identify as load changes, the bus voltage changes. Okay. And yeah, so the bottom line here is that the cellular simultaneous recurrent neural network architecture has a 50% reduction in the number of weights for a 12-bus network. Of course, this will scale up rapidly as you go to larger networks. The second problem I'd like to share with you is the generator speed prediction. In this case, I take the IEEE 68-bus system. And those of you that are working in power system oscillations are maybe familiar with this network. We basically have 16 generators as indicated in a 5-area system. And we want to basically predict the speed deviations of this synchronous generators for one or more reasons, either disturbances, load changes. Yeah. So you can model each of these generators with a cell, since the emphasis is on the generator speed deviation or frequency. And of course, if you take 2 neighbors for each cell, then the 68-bus system splits into islands, and we don't want that. We want to still keep the system as a complete system. So in some cases, we use 3 inputs. And then when that 3 inputs completes the CCN as a one system, one network. And then basically, one of the things we do in power system oscillation is we basically look for the electromechanical oscillation that's on each of the generators, that exhibits on each of the generators, and then the corresponding damping based on what kind of controls we have, power system stabilizers turned on or off. So you can see what's shown here is that the frequency identified by the PMU data and the damping is also what we pick up from the CCN waveforms. And when we do the time domain, frequency domain analysis, the frequencies are identified, which basically tells us that the CCN has captured the electromechanical oscillation dynamics of the 68-bus system. And again, the learning of the CCN is sparse, as shown by this graph. And basically, the difference between the red line and the green line is that there are two types of neural networks we have used in the cells. One is a simultaneous recurrent, and the other one is just a multi-layer perceptron. So depending on the complexity of each node, the injections at each node, you might need a dynamic shallow neural network or just a feed-forward network. So again, due to the sparse learning, you can see that cell 3 learns for more time compared to, let's say, for example, cell 6. Yeah. So this is again one of the advantages of the CCN. The learning is asynchronous, it's distributed, so you don't spend the same amount of training time across the AI model, which is what you do with the deep neural network. So again, we put a performance index to compare the performance of the CCN against a time lag single neural network trying to do the same job here, as well as the multi-layer perceptron. And you can see the performance index here shows us that the CCN for a 16 generator problem has at least 16 times improvement in terms of the mean squared error as well as the number of parameters. Yeah. So 16 times fewer weights than a time lagged recurrent neural network, and that translates to less energy for learning. Yeah. So with that, I will summarize and I will open up for questions. The cellular computational networks are basically massively parallel and highly scalable dynamic recurrent architectures by nature because of the cell connectivity. With the CCN framework, learning takes place locally at the cell level. And then, of course, each of the cells learn at their own pace, asynchronously. So some may require longer training times, and some may be quick to learn to meet the set performance thresholds. And the cells collaborate to achieve learning of the dynamics of a complex system. So again, going back to my very early slides, the complex system is divided into subsystems and components, and you architect the AI model based on the structure, right? So CCN have fewer synaptic weights or fewer parameters, since each cell implements compact or shallow neural networks. And online CCN operation and its learning is simpler, resulting in less computational energy and training time overheads. And CCN is a sustainable and a scalable AI implementation approach for complex networks and systems. And I think I have a couple of announcements after that. So one of the things, I'm a vice president of industry of the International Neural Network Society for Industry Relations. And if you liked what I presented, then I invite you to join the International Neural Network Society, where we basically go from all the way from brain-like learning to neuroengineering to crafting energy efficient AI. So you will probably like to know what the society does. And here's a QR code to join in. And of course, the INNS partners with IEEE CIS. So we have a flagship AI conference, the Neural Network Conference, known as the International Joint Conference on Neural Networks, IJCNN 2027, which is held every year. And as the general chair for the IJCNN 2027, I'd like to invite you to submit your papers to IJCNN 2027, which will be held in the beautiful city, mother city of South Africa, known as Cape Town, 14th to 18th June 2027. So with that, I'd like to thank you for your attention, and I will be glad to take any questions and comments that you may have. Thank you.
Thank you, Dr. Murthy.
You're welcome.
Yep. Please feel free to drop your questions in the chat, or you could unmute yourself and ask Dr. Murthy directly your questions. Yes, as we wait for the questions, I have one question, Dr. Murthy. You probably
Yes.
covered it in the introduction of the CCNs, but how does the
Yeah.
connection between those units determined? Um,
Yeah.
in
So
your
so yes, that's a great question. So if you look at this IEEE 68 bus system, right? So we are trying to model, for example, here the generator dynamics. So since we're interested in the generators, you put the cells on the generators. Okay. So let's go back to I had a diagram there. There it goes. Okay, here we go. Yeah, so this diagram basically shows us how the cell sits on top, basically each generator with its own cell. Okay.
Mhm.
So, and the topology for the connectivity is the topology of the power network. So the 68 bus system is connected, how the buses are connected between each other, that's how we would connect the cells as well. So depending on what you're trying to do, so depending, as I showed you, you can have multi-layered CCN. So in this case, we are looking at the speed layer, the speed deviation of the generators. So we would basically look at the electrical proximity of the generators and connect them. And you can do coherency analysis, for example, because some of these generators will oscillate together and some will oscillate in different groups. And of course, we can bring coherency grouping and so forth to better model how the generators oscillate.
Thank you, that makes sense.
So understanding the physics of the system helps us to develop this AI model to basically solve what we're trying to look for, rather than just randomly throwing AI models that consume a lot of energy and trying to figure out. He basically solved half of the problem for the AI model, make the AI model more efficient, energy efficient.
Okay.
I hope I answered your question.
Anyone else has a question? Yep. Yeah, there are no questions. I think this is a very new topic. It's a timely topic too. I don't
So the other
have
thing is,
like, I don't want to misquote, but I think there's been some analysis on how much water is being used and how much energy is. Oh, okay.
say that again, Ali.
Now, I was just saying, like, this is a timely topic. Currently there's a lot of scrutiny after these all the LLMs and ChatGPT and all of this became a trend. There's scrutiny on how much power and water they use. I think that's I don't know the exact number, but it was they were comparing against a simple query versus an AI query. Nowadays everything has AI.
Yes.
And there's also
Yeah.
like questions on Google is trying to auto create like summaries. That's not needed for all queries, but they kind of keep doing it. And these things add up. And I think,
yeah, I think if you do one Google search, just a traditional Google search, and if you do a Google search with ChatGPT, the amount of energy consumption is 10 times at least.
there we go. Yeah, exactly.
Yeah. And yeah, so the other nice thing about the CCN is that now you have this slide in front of you and you can see the cells, and you can basically pull the output of any cell with respect to the rest of the cells. So in other words, you can explain why you're seeing the different output behaviors at the different cells. And you can say, look, cell 5 is behaving very close to cell 4 and 3. That's because they're in proximity. Yeah. And maybe something happens in cell 5, maybe that generator undergoes a fault, and then you're going to pick that up right away in the neighboring generators. So C4 and C3 will pick that up. And now you can look at this the inside of an AI model from a spatial point of view, from an electrical spatial point of view, right? So this allows us to explain the AI model, why the outputs are seen they are based on, then we can map it to the topology of the power network, and then it'll be well aligned. Whereas if you have a deep neural network and you have these multiple outputs, you don't have this inside. Okay. And this is, so in a way, the CCN also enhances the explainability of the AI model. Yeah, so that's the other feature that we can see out of the CCN development. Yeah, it's a beautiful framework. And again, the cells don't have to have neural networks. They can have, some of them can have neural networks, some can have, a traditional mathematical algorithm, a differential equation, a differential algebraic equation, and so forth. So it's a framework where you can throw in different kinds of computational algorithms, and you can basically have a heterogeneous computational model. And that can even further save some of the energy consumption. Some don't have to learn. Some of the cells may have algorithms that don't have to undergo learning. So you can further improve, enhance the energy efficiency of the AI model. So again, it's left to the designer or the developer to tailor the design such that such computational models are more energy efficient.
Absolutely. Yeah, now my background is not, I think at some point, big disadvantage of neural networks was around the explainability, especially for power system. And there was a lot of research around physics-informed machine learning. But I think this kind of bakes that into the existing architecture. So really good work.
Yeah.
Thank you.
Yeah, and the more physics you know about the system, the more the CCN becomes really a snap-on. Yeah.
I think a good, leading question to this is, what is next steps to this? Like, where is this direction going? Are you working with any collaborators?
Yes.
Any future to this?
So we have done a lot of different applications, which I didn't share today, but even transmission, topology processing, state estimation, dynamic security assessment, all of those are all possible with the CCN framework. So of course, those of us that work in energy management, EMS applications, and power system operations know how important it is to have a good model. So a transmission network topology processor can be developed based on a CCN, and then you can use signals, even breaker status, and all of that can be built all the way from bottom up. And you can have a TNTP, transmission network topology processor, that can be driven off the PMU data, okay, very fast. Okay, and if you have that capability, then you can do distributed linear state estimation. Okay, and we all understand how state estimation and distributed linear state estimation can change how we operate in control centers with variable and intermittent energy sources, right? And then the next step is how we can use the TNTP and the distributed linear state estimator to do dynamic security, distributed dynamic security assessment. And this will basically looking at not only at the network level, at the area level, but also at the substation level. So all of that can come together very fast, and you have, you want to know why you are seeing something at an area control center. You can trace it back right away to the substation where this got triggered. So fault tracing, disturbance tracing, where you need to mitigate, where the control actions can be taken, all of this with the CCN framework. The CCN framework is a hierarchical distributed architecture. And that's where I think the intelligence comes in. So if we are looking at making a power grid an intelligent power grid, then you need to have hierarchical distributed architecture. And of course, we all understand we need to work with AI, but we cannot work with large AI models that consume a lot of energy, that are not resilient, that are subject to attack itself. We need resilient AI and sustainable AI, still scalable. I think this is where the CCM fits that quite nicely and fits the power system problem in the hierarchical architecture, the huge, huge network that we have in a power system. So this all nicely comes together, in my opinion. Yeah.
Absolutely. I don't still see any questions. I'll give one last call for any questions. And if not, I'll wrap up the call.
All right. So if there's any questions, anybody feel free to email me, gkumar@ieee.org. Be glad to talk to you.
Perfect. Thank you, Dr. Murthy. Really appreciate you spending time with us today. This is a great topic. We learned a lot today. But appreciate your time.
Thank you.
You.